Welcome to our presentation, and thank you for taking time to participate. The presentation will discuss the past, present, and future of real-time simulation. By reviewing the past, we will introduce different techniques applied to real-time digital simulation and show how capabilities have been developed over time. The present will show the state-of-the-art in real-time digital simulation, while the future will discuss anticipated market demands and the developments that may result. So we will start from the past. The development of the RTDS simulator began in the 1980s at the Manitoba HVDC Research Centre. Researchers there wanted a tool to investigate the behavior and performance of HVDC controls, and the best way to do that was to use a real-time simulator. During this period, HVDC projects were being developed at a rate of one every few years or more. At the time, the only real-time simulators were based on analog technology, physical scaled-down electrical models of the power system. Analog simulators were expensive to purchase, operate, and maintain, plus they were physically large. As a result, only a very few institutions had the privilege of such devices. In addition to being expensive, analog simulators did have some significant limitations. One of those was the limited ability to adjust parameters of individual components. For example, the parameters of a machine. It was virtually impossible to have the scaled-down machines behave the same as their large counterparts, never mind being able to freely adjust their parameters. The losses of the analog simulators also tended to be larger than those of the actual networks and yielded optimistic results. Basically, they were overdamped, particularly if the nominal operating voltage of the simulator was low. Simulators operating at less than approximately 50 volts normally use special loss compensation components, so-called negative resistors. These were difficult to tune. Researchers at the HVDC Center did not have access to the funds or the space for an analog simulator. However, they were very familiar with the numerical methods applied by Dr. Dommel for the solution of electromagnetic transient, or EMT, simulation through their work in developing EMTDC. For those of you that are not aware, EMTDC is the original name of the PSCAD simulation engine. PSCAD was originally the name of the user interface, and it was used with both EMTDC and RTDS. The other important factor in the development of the RTDS simulator was the release of the first floating point digital signal processor, an efficient and deterministic platform for real-time simulation. The original TPC processor card for the RTDS was developed in the early 1990s and ran at 11 MHz with 2 DSPs per card. The TPCs and communication cards that made up the RTDS rack were connected together on a common 32-bit backplane. At that time, transferring one number over the backplane required 175 nanoseconds. That might not seem like much time, but if there are 100 numbers to transfer, that took 17 microseconds just for communication and was a significant portion of the simulation time step. Considering the performance of the processors and communication, ultimate efficiency of code and communication usage were required to achieve real-time simulations. In this early platform, each node required one DSP, which limited the size of the network that could be included on each rack to around 4 to 5 buses. It was not possible to decompose the network matrix in real time, so different matrices were stored to represent each switching state. Depending on the switching state of the network, a different matrix was selected for the network solution. 2 to the n matrices, where n is the number of switches, needed to be stored. As a result, no more than 10 single-phase switches, breakers, and faults were permitted per rack. All components were included as fixed admittance elements with parallel current injections, and nonlinearities, such as saturation, were represented using current injections. Only discrete analog and digital signals were available on the earliest platform. Optical isolation was provided on the boards, but the I/O cards connected to the processing units via electrical cables. The development of real-time digital simulation opened up new possibilities for the development and testing of protection and control equipment. And perhaps even more important, the reduced costs and size meant more organizations were able to purchase real-time simulators. Digital simulation meant network models were relatively straightforward and quick to develop compared to analog simulators. There was more flexibility in modeling than with analog simulators, and tests became trivial to repeat. The networks were limited in size and complexity, though. Studies generally focused on the scheme under test, for example, the HVDC or fax device, with minimal surrounding network representation. By the late 1990s, HVDC projects were typically 1 to 2 projects being developed each year. The second generation of RTDS simulator brought new modeling capabilities. The new platform incorporated 3 DSPs on a single board operating at 40 MHz. A new network solution was developed whereby part of the subsystem matrix was decomposed in real time and stored matrices were used in the other portion. The 3PC network solution used 2 cards, 6 DSPs, directly connected to one another and allowed up to 21 nodes per subsystem with 28 single-phase switches. Having part of the network matrix decomposed in real time offered new possibilities. Component models that previously used numerical interfaces could be embedded in the network solution as variable admittance elements. An important example was the thyristor valve group. Embedding the valve group in the network solution improved numerical stability and allowed valve faults to be properly represented. A new technique called improved firing was also developed to provide continuously variable firing angle for thyristor valves, down to a resolution of 1 microsecond. Customers preferred to use the increased processing power to expand the network models rather than to reduce the simulation time step. Commercial projects like HVDC continue to run with simulation time steps of 80 to 100 microseconds. In about 2003, there was a significant shift in the simulator platform with the release of the first RISC processor-based card. The RPC operated at 750 MHz and was quickly replaced by the GPC, which ran at 1 GHz. These clock speeds and highly efficient instruction sets provided a tremendous lift in simulation capabilities. With the RISC platform, the entire subsystem matrix was decomposed in real time, and the size was increased to 54 and later 60 nodes per subsystem. The limit on the number of switches was no longer a relevant consideration either. Larger scale multi-rack simulators were installed to model networks with many hundreds or thousands of buses. Even with the larger and more complex network models, the simulation time step was reduced to 60 to 80 microseconds. Around the same time, a new family of I/O cards was also developed. Separate cards were developed for analog and digital input and output. These cards were all connected to the processor units using optical fibers and could be connected to one another in daisy chain. A big advantage brought by the new design was that the I/O cards could be located remotely from the simulator by tens of meters to minimize the length of electrical cabling. Decomposing the entire matrix in real time provided a great convenience and allowed for more advanced modeling techniques. The 3PC network solution did provide real-time decomposition of part of the matrix, but there were rules that had to be followed on the placement of the nodes, and the subsystem size was relatively small. The smaller subsystem size meant that the networks had to be divided up into many parts, and it was not always possible to find lines or cables long enough to break the system up without introducing inaccuracies or decoupling elements. Since the entire matrix was being decomposed, any components modeled could be connected to the network solution as a variable admittance element rather than fixed admittances and current injections. The variable admittance technique proved to be more stable for the representation of nonlinearities such as saturation and surge arresters. The increased processing power provided by the GPC also meant that even more complex models could be developed. Asynchronous machine model with internal faults, 12 pulse valve groups with 3 or far winding transformers, etc. Support for multi-rack simulators was also increased to 60 racks. By the mid-2000s, manufacturers were often developing 2 to 3 HVDC projects at the same time. In the early 2000s, force commutated valves using IGBTs started to be used in FACS and HVDC. It was clear these installations needed to be represented in the RTDS to support testing of their protection and control schemes. As a result, small time-step subnetworks were developed to operate with time steps in the range of 1 to 3 microseconds. The small time-step subnetworks were interfaced to larger network models so as not to limit the size. The larger network operated with a time step of 60 to 80 microseconds, while the area needing higher fidelity operated at a time step of 1 to 3 microseconds. The small time step subnetworks used LC switching to avoid the need to decompose the admittance matrix. LC switching uses a small inductor to represent the on state and a small capacitor to represent the off state of a switch. The value of the L and C are chosen such that for a particular time step, the corresponding admittance value for the L and C is the same, therefore avoiding the need to decompose the admittance matrix to represent switching actions. Only the current injection needed to be changed. In addition to LC switching, small time-step subnetworks used a special, limited subset of components to keep the time step low. One limitation of LC switching was the creation of fictitious losses that limited the maximum switching frequency to approximately 3 kHz. Another industry trend around 2005 was the move to implement IEC 61850 Goose messaging and later sampled value data streams input to protective relays. The GTNet was developed to support Ethernet-based protocols like IEC 61850. In 2011, the fifth generation processing platform was released, the PB5. The PB5 included 2 RISC processors operating at 1.4 GHz. Together with this development, the communication backplane was augmented using optical fiber connections. The higher processing power and increased communication bandwidth allowed the subsystem size to be increased to 90 nodes. The typical time steps of simulations was also reduced to the range of 50 to 60 microseconds. Around the same time, the fixed topology 2 and 3 level VSC converters were developed for the small time step subnetwork using resistive switching. These converters were able to test PWM controllers operating at 40 to 50 kHz. As MMC-based FACS and HVDC schemes were being developed, it was necessary to provide a means to test the protection and control equipment. Due to the dynamics and protection requirements of these converters, a time step in the range of 3 to 5 microseconds was required. After much study, it was determined that an FPGA was the best means of representing these converters. Schemes with 3,000 submodules per station of a symmetric monopole were being considered. Therefore, conventional I/O was impractical as 3,000 submodule voltages would have to be provided to the controller and would have required 250 analog output cards per station. It was decided to use Aurora, an open-source, high-speed serial protocol to communicate between the RTDS and the controls. The data carried the firing pulse pattern of each submodule over one optical fiber and returned the submodule voltages plus valve current to the controller over another fiber, an RX-TX pair. Over time, the use of Ethernet protocols became more widespread in the power industry. In response, the GTNet X2 card was developed and additional protocol support was added. Additional protocols included DNP and IEC 6870 SCADA protocols, IEC/IEEE 60 255-118-1 synchrophasers, Modbus, as well as generic TCP/UDP socket communication. Testing of PMUs and streaming of synchrophasors required the simulator to synchronize to the same time reference as the external equipment. The GT-Sync was developed to support this by accepting a number of different time reference protocols to which the simulation time step could be synchronized. Now let's focus on the more recent developments, the present. The most recent platform, NovaCore, was released in 2017. NovaCore represented a state change in the technology, with each unit having a 10-core RISC processor operating at 3.5 GHz. The communication backplane was eliminated and replaced by extremely fast, on-chip, core-to-core communication. The combination of the increased processing power and communication bandwidth allowed the subsystem size to be increased to 600 nodes. Essentially, the maximum size of the subsystem is no longer a relevant consideration when modeling a transmission network. The power of NovaCore has also resulted in the typical simulation time step being reduced to the range of 20 to 40 microseconds. Today, a single manufacturer will run more than 5 HVDC projects at the same time. Together with the NovaCore platform, RTDS Technologies released a true multi-rate simulation environment consisting of superstep, mainstep, and substep. Mainstep is the standard simulation environment with a typical time step in the range of 20 to 40 microseconds. If a portion of the circuit requires higher fidelity, such as a converter with higher switching frequency, it can be modeled in substep using a time step that is an integral multiple smaller than the main step. If a different portion of the network can be represented with lower fidelity, i.e. larger scale network equivalents, they can be modeled in superstep with a time step that is an integer multiple larger than the main step. Substep replaces small time step subnetworks and provides significant advantages. 1. Substep decomposes the admittance matrix every time step. 2. Resistive switching is used instead of LC switching. The use of resistive switches makes the performance of substeps more predictable. For example, there are no unexpected spurious oscillations introduced by new switches. It also means that the switching losses can be set by the user. 3. Substep subnetworks can have as many as 60 nodes. 4. All components are supported in substep, not only special optimized components. As time has gone on, our largest customers continue to expand their simulators, and we needed to go beyond the limit of interconnecting 60 chassis and/or racks. The latest generation GBH and IRC switch support interconnection of 144 chassis and/or racks. These large simulators now model thousands of buses in real time and support the investigation of network security and reliability. Converter-based devices are becoming more important in our networks. They are used in renewable energy, energy storage, electric vehicles, etc. Some of these devices are lower power devices, and because of the introduction of low-loss devices like silicon carbide-based IGBTs, the switching frequencies can be quite high. Devices like solid-state transformers using dual-active bridges also require very high resolution. Motivated by these factors, RTDS Technologies developed the Universal Converter Model, or UCM. The UCM has a number of different converter topologies available, and it provides different options to control them. The simplest input form is to provide the modulation waveform, whereby the model acts like an average model. Alternatively, the model can read raw firing pulse input once per time step, and the model will behave much like the models previously available for small time step and substep. The most exciting option for the UCM, though, is the improved firing input. Improved firing input captures the firing pulses that arrive during a time step and calculates an effective duty cycle for the respective device/switch. Multiple turn-on, turn-off transitions per time step are allowed. The GTDI V2 card is used when external firing pulse controls are tested. The GTDI captures the firing pulses with a resolution of 10 nanoseconds. The improved firing very accurately reproduces the converter characteristic harmonics and introduces minimal non-characteristic harmonics. The comparison with PSCAD is also very good. The UCM can be used in either substep or main step environments. When operating in substep, the UCM can accurately model converter switching with PWM in excess of 100 kHz. Even in the main step, with a time step of 30 to 40 microseconds, the UCM can accurately represent PWM switching to the range of 10 kHz. Large-scale simulation centers are becoming more common. The simulator shown here includes 40 Novacore chassis and can represent networks with nearly 4,000 buses and 20 HVDC links. The simulator was purchased to validate wide area protection control schemes, ensure coordination of HVDC and AC system control, as well as investigate network stability. Not all organizations have the funding for such large simulators, though, so network equivalents can be important to keep the size and cost of a simulator down. A number of companies have used static fundamental frequency equivalents developed using programs like PSSE and Aspen. These equivalents can work well for some studies, but they are not able to handle a wide variety of network conditions. Essentially, these network equivalents are static and do not adapt to different load flow scenarios brought about by changes in the main network. An alternative is to use an EMT-TSA hybrid simulation, where part of the network is represented in the EMT domain and the other part modeled using TSA or RMS techniques. We are presently adding support for this directly on the RTDS simulator, and other institutions have done it using a PC to run the TSA and connect to the RTDS simulator. PowerTech Labs, for example, created a TRI interface between TSAT and the RTDS. A university in Germany is also developing an interface to PSSE. Another possibility for network equivalencing is to represent large-scale networks in the EMT domain using SuperStep on the RTDS. As converter-based generation and devices play a larger role in our power system grids, the industry is realizing that classical TSA RMS modeling does not accurately predict the behavior of our grids. More and more organizations are adapting to EMT simulation for the study of the stability and performance of our grids. Interloop controls like PLLs can be accurately represented in EMT simulation. Very detailed protection models can be represented. Unbalanced phenomena are easily modeled, etc. These things are either not possible or more difficult to model using TSA and RMS simulation models. EMT modeling is critical to the decarbonization of our grids, since virtually all renewable generation and energy storage schemes are connected to the grid via power electronic converters. EMT simulation allows the testing of individual schemes as well as investigation of possible interaction between schemes. A combination of modeled and physical protection and control are commonly used in these investigations. To aid in the deployment of converter-connected schemes, vendor black box models that run on real-time simulators are required. These models must include the interloop controls. They should ideally use the vendor original codebase, and they must not reveal any proprietary information. Using vendor black box models will ensure more accurate representation of these schemes through all operating conditions when replica controls are not available. Now let's move on to the future. We have talked about the last 30 years of development for the RTDS simulator, but what about the future? How will it progress from here, and what are the market drivers? Decarbonization of the power grid is a large driving factor for the simulation industry. Decarbonization requires the deployment of renewables and energy storage, as well as the reinforcement of the grid with HVDC and fax devices. The sheer number of schemes that must be installed in the next 10 to 15 years is staggering. If we are to achieve these goals, efficiencies must be found to shorten project cycle times. An immediate goal to shorten project times is to create fully digital interfaces to control equipment. Such a connection would allow the core control algorithms and logic to be tested at an earlier stage of the project. It would also make it possible to reduce the physical size and cost of replica simulators.
For the reasons mentioned previously, primarily the increased penetration of converter-connected devices in the grid, it is expected that EMT simulation will replace TSA modeling for grid planning and grid studies. These simulators will not need to operate in real time since there will not be any external equipment connected. Near or even faster than real-time operation will be targeted. Running multiple simulations at the same time for contingency analysis will increase efficiency. To support this in a scalable fashion, deployment to a private or public cloud will be advantageous. Data security will be a primary consideration, though.
A next step after using large-scale EMT modeling for grid planning will be to use it for direct support of grid operations. Here, grid operators would run contingency analysis at regular intervals to determine their best course of action should certain events occur in the network. Support of grid operations would require that the current state of the network, i.e. the load flow and switching state, be read from the SCADA scheme. It would also be necessary to seamlessly import protection and control models from vendors to accurately represent the operation of the grid. Protection settings would be read from the utility's protection settings database. It can also be imagined that such simulations could be used for continuous training of AI control for automated or semi-automated grid operation. Considering the critical nature of some large-scale installations, for example HVDC, large wind farms, etc., new regulatory requirements may be put in place requiring all software and firmware updates to be tested in a realistic environment, for example using replica simulators, before they could be placed live in the grid. This could become a driving factor in the adoption and deployment of real-time simulators. There are always efficiencies to be gained through consolidation of tools. It would be a distinct advantage if one tool could cover a large or the entire spectrum of simulation requirements, right from short circuit analysis, relay coordination, load flow, TSA, EMT, real-time, etc. Today there is a push for common data formats between simulation programs, but that does not address all efficiency requirements. The use of a single tool for all simulation requirements would clearly be beneficial. One of the biggest issues for simulation results is the consistency and validity of data. The data used in different simulation domains needs to be consistent with one another, and the data must reflect reality. Therefore, the use of one simulation platform, or at least one common database for various simulation tools, is something to strive for. The methodologies to validate simulation data also need to be improved. Ideally, techniques should be developed to validate parameters using online measurements. An example of this could be that each time there is an action or transient in the grid, it would be used to validate as many simulation parameters as possible. Thank you for taking this journey with me through the past, present, and future of real-time digital simulation.